Hello, today I am going to do a review video about acid-base reaction. Now this video is going to break down into two parts. In the first part, I will focus on the conceptual understanding of the acid-base reaction, and then later on I'll do the second part of the video, which is about the titration graph. Now this review video is focusing on the strong acids reacting with strong base, like sodium hydroxide. Compare that to weak acid, like acetic acid, reacting with strong base. There's always a confusion about this topic. And why is that confusing? First of all, because in Chem 2, there's really a lot of math. And if you look at the textbook, you'll find that almost every single page has a calculation. And because of that, that kind of mislead almost everyone to think that Chem 2 is all about math. And the truth is, it's not. And this confusion started from Chem 1. And when we did stoichiometry, we always ask you to calculate how much solution do we need to complete the reaction, or how much of the product is going to be produced. We tend to focus on that quite a bit. And that is really where the confusion came from. And when we ask you to calculate, we always tell you, hey, this is the product you're going to get. Tell me how much you're going to get. If we change the question and asking what product being produced, what if we have different amount of reactants, which one will be left over, and things like that. With that nature, students tend to struggle a little bit, and that is really the foundation of the confusion, because we focus on something easy rather than something that's necessary. So I'm going to show you a couple of problems, what I mean by we go the easy route. For Chem 2, to understand how strong acid-base reaction different from weak acid strong base reaction, we really need to focus on the chemical behavior and what is really existing in a solution. The reaction progress is really the most important. What is changing? What is reacting? So I'm going to start with the confusion where you were misled from the beginning. So let me show you a problem that you have seen that many times. So in this problem, you see there's a certain amount of hydrochloric acid react with sodium hydroxide. What volume is required for the sodium hydroxide to reach the equivalent point? Well, I'm going to just write the formula HCl, AQ, acetic acid, HC2, H3O2, AQ. So what you always do is write the balance equation. So acid, HA, so A stands for chloride for the first question, it stands for acetate for the second question, and then we add with NaOH, AQ to produce sodium chloride or sodium acetate. So I use A to stand for anion plus water. And then with the balance equation, of course, this is 1-to-1 ratio, or have coefficient of 1. So just to give you an easy example to understand why this is kind of misleading, because you look at both questions, you have the exact same balance equation. So your calculation will look exactly the same. So you calculate mole of acid in solution. That is the step 1. And based on the mole of acid, you use the mole ratio, acid to mole base ratio. So that will be 1:1 in this case. And step number 3, using the mole base and the concentration, you have mole base divided by volume of base. You get the concentration, in this case 0.10. Both questions, you go through the exact same step. But in Chem 2, when you do titration graph, they use different method depending on the circumstances. So there's a lot of similarity in terms of calculation between the two. So that's where the confusion started. In Chem 2, they are so different. So this is one of the examples. I'm going to show you another example. Let's go back to the second focus, why it was confusing. The confusion is focused on the product, and you were told what product being produced. You look at these two questions. Hydrochloric acid react with sodium hydroxide. What will be the concentration of sodium chloride at the equivalent point? Sodium chloride is the product of this reaction. Acetic acid react with sodium hydroxide to produce sodium acetate. So if I write the equation, you will find the equation look exactly the same. The only difference is on the product. Okay. So either HCl to produce sodium chloride, or acetic acid to produce sodium acetate. So the calculation is exactly the same. So you start with the amount of acid. So step 1 will be starting with mole of acid. Step 2 will be the mole ratio, mole acid to mole sodium chloride or sodium acetate. Ratio will be 1:1 in this case. Step 3, mole of NaA. So of course the problem I have in this question is I did not hit the microphone, is that if I give you the concentration and you have the total volume, so since it's 1:1 ratio, you find out 40 milliliter of sodium hydroxide, so the total volume will be 0.080 liter. Then you're going to find out the concentration. So this is the problem you tend to see a lot in Chem 1. And because those questions are just so similar regardless it's strong acid or weak acid, and you don't see the difference. So Well, what's the problem? So we really need to focus on is how the chemical behave and focus on the progress. So I gave you a few minutes of review about the Chem 1 calculation that you have done before. We are not saying that it is not important. You may use it at some point. You might calculate one data point or so in a titration graph. But the main thing is, how do you construct a titration graph if you don't know the rest of the points? So to know the titration graph really well, we are going to look at the first missing link. So if I have this question, it's still an identical question. If I have 1 mole of hydrochloric acid titrate with sodium hydroxide, how many moles of HA, that's hydrochloric acid, A minus, that means it's chloride, left at the equivalent point? And I have the second question, it is identical. So I'm going to pause for a minute and see which answer you're going to pick. Okay. If you have not made a decision, you might want to pause the video. I'm going to tell you the answer, otherwise the answer will be D. This is a variation of so-called limiting reagent problem. It's just such a big word, it scares a lot of students, I know. Limiting reagent just means which one is being consumed first. Think about, you have acid being titrated by using sodium hydroxide. That means you can assume you have unlimited amount of sodium hydroxide to consume the acid. So at the end of the reaction, the amount of acid left over should be 0. The reason I ask this question is, well, in the classroom I ask this almost every semester, and I found that students tend to have two very popular answers. One is A, the other is D. And almost 50-50. Half will pick A, half will pick D. The reason students pick A is that they think about titration graph. When you keep adding hydroxide, they did not think about that the acid is actually changing. At the end, you know you get chloride or acetate. But the acid part is being consumed. You cannot create something out of nothing. The amount of A minus that was present, at the end, you still have only 1 mole. Okay, so that's the right answer. 1 mole of this changed to 1 mole of that. This 1 mole will not exist at the end. Okay, so that's missing link number 1, is to understand that what is being consumed, in other words, what is changing. Okay, so the reaction occurs by having hydroxide reacting with this, so this has to be changing. Okay, well, how does it change? That is missing link number 2. This is also one of the questions tend to be quite unpopular, I would say. Students don't like being asked how to write net ionic equation. And all textbooks are very methodical and tell you exactly what to do. And that's very unfortunate because of the way it's written, and students tend to misunderstand what that means. So I'm going to do these two net ionic equation. Okay. So the first one I'm going to do is hydrochloric acid. A little boo-boo. I shouldn't use parentheses. Okay, so that is the molecular equation. So what happens when you put put hydrochloric acid in water? The reason you got hydrochloric acid is because in water it's 100% dissociated. Okay. So this looks quite familiar. Sodium hydroxide is also a soluble compound. That means it will dissociate. So on the left hand side, that's what it looks like. On the right hand side, you have Na plus, Cl minus, plus H2O. Okay. And then what you would do is to cancel the ion, end up with this. So Na plus sodium cation and chloride anion are what we call the spectator ion. Okay. What's the meaning of spectator ion? That means they are sitting in the solution and looking. So the first thing we want to clarify is what's the meaning of acid. Acid means the available protons. Okay, so this is your acid. Not HCl, but H plus. How much H plus do you have? That is acid. Okay. That's number of protons. You learn the definition of Arrhenius and Bronsted-Lowry acid. So that is the acid. Okay. The number of protons. So I'm going to show you the picture. What it really looks like is this. HCl right up here. Once you put that in water, it is H plus and Cl minus. They are all separated in water. What happens when you add sodium hydroxide? Sodium hydroxide solution is this. If you add sodium hydroxide solution, you're adding H plus and Na plus. They are already separated. So when I say conceptual understanding, is to understand what is happening in the picture. Okay. So what happens when you put sodium hydroxide into hydrochloric acid? Well, in this case, I only add a little bit. I did not complete the reaction. So these two would bond together. So I do have Na plus. So you see missing space, you have H2O. Okay. So once you put sodium hydroxide in water, this doesn't exist anymore. This is what it looks like. All the protons are free from the chloride to begin with. That's what this equation tells you. Hydroxide in water could just go grab the H plus available to form water. That's the meaning of net ionic equation. Okay? It shows you how reaction happens. Okay. So at the end of the reaction, what's going to happen? So if I plot the titration graph, I'm going to do the titration graph in the second video, but I want to show you what it would look like. At the end of the reaction, the pH would end up at pH 7 for strong acid, strong base reaction. Okay, at pH 7. So let's look at a little bit of what kind of redundant, but hopefully it helps you understand more, is to remember this picture. I'm going to look at the progress. I have 4 hydrochloric acid molecules. See, 1, 2, 3, 4. So each time I add 1 hydroxide molecule into the same part, gradually see what happens. So at the beginning, I did not add any, so I have, so without these two, so I will have 4 apologize, the graph a little bit too big. So at the beginning, I did not add any hydroxide. I have 4 free H pluses. The chloride also free, so that 4 to 4 ratio. Okay, so 1 to 1. What happened after I add each hydroxide? So after I add 1 hydroxide, you realize that one of them become water. You have 1, 2, 3. So you have 3 H pluses, but you still have 4 chloride. If you keep adding more hydroxide, and other H plus is going to react, so you have that down to 2, but number of chloride never affected because they were free to begin with. So you keep going. Eventually, it will be completely reacted. Okay. Well, if I use mole, so if I assume it's 1 mole, so I got 100%. 0.25 is a quarter of a mole, or you can look at it as 25% ratio. If I add this amount, the amount of H plus will reduce because hydroxide, whatever you add, is going to react with H plus. And you see gradually reduce, eventually go to 0. For the free chloride ion, they never change, because they're spectator ions, so they don't do anything, just sit there from the beginning. That is how strong acids react with strong base. The ions are free, hydroxide just come in and grab the H+. Okay, so how is that different from the weak acid? Acetic acid will have net ionic equation like this: C2H3O2 AQ plus NaOH AQ to produce NaC2H3O2 AQ plus H2O, which is a liquid. Okay, so continue. What happened to the acetic acid in water? Practically nothing. It may dissociate to slight degree, but the vast majority stays as a molecule. That is the huge difference between a strong acid to a weak acid. Strong acid, the proton is free from the beginning. Weak acid, the proton is not free. So it's held on by the acetate. So Na plus OH minus. So I know I'm running out of space, I'm going to use the bottom. So the right hand side will be Na plus acetate ion plus water. So when you try to cancel, this is really the bad word to use, is cancel. You cannot cancel chemical because the chemical is in the solution. This whole equation, every single piece of this equation is in the same beaker. So instead of saying cancel, I'm going to say that this is unchanged. So what you end up getting is this: HC2, H3O2, AQ plus OH minus plus C2, excuse me, not plus, is arrow, C2H3O2 minus plus water. Sodium plus is the spectator ion. Okay. We talked about before, net ionic equation tells you exactly what happened in the solution. So you have to picture what is happening. The proton is not free. So I'm going to show you the beaker. I have 4 molecules again. So what happened when you add sodium hydroxide? Well, sodium hydroxide has sodium and hydroxide already separated. Strong electrolyte, they are separated to begin with. So now, when you have NaOH, what does the OH do? The OH pull the hydrogen away from the acetate. It is tug of war. the stronger win. Okay, the stronger one wins. So OH minus is a stronger base than acetate. That's why it is strong enough to pull the hydrogen away. So what you end up getting in the product is this. Na plus will still stay in the solution. That's the mineral spectator ion. It is there, it just doesn't do anything. So you end up with CH3, COO negative, and H2O. And you end up with sodium acetate because hydroxide pull the hydrogen away, and the cation, anion have no choice, but they become together passively. Okay. So you see they are quite different. Compare the strong acid reaction is that the hydrogen is already available. But for weak acid, the strong base has to do some work. It has to pull the hydrogen plus the proton away from the acetate. Well, the acetate, if you heard of this term, in this case, CH3COO minus is the conjugate base. It's a base, but it's weak base, conjugate base of acetic acid. Okay, it's a weaker base than hydroxide. That's why the reaction favors the right hand side here. Okay. All right. So I'm going to do the exact same thing like H plus. Excuse me, HCl, the strong acid. If I have simple diagram for acetic acid and add hydroxide ion one at a time, how does that work? Okay. So at the beginning, we have 1, 2, 3, 4. Go down a little bit. 1, 2, 3, 4. We have 4 acetic acid. And there's no acetate ion. Before you add hydroxide, you have no acetate ion. Oh, I use the word protonated deprotonated form. I don't use H plus and Cl minus. The reason is this. If you look at this diagram, the acetate is actually in every single one of them. The only difference between the acetate and acetic acid is that acetic acid has a proton. So the protonated form of acetate is acetic acid. The reason I use this term, you're going to see, ultimately it's come down to a so-called ratio. And when you have the presence of a weak base and a weak acid, this is the important term. It's called buffer. Okay, having the presence of both weak acid and its conjugate base is also weak base, you have something called buffer. Strong acid, strong base reaction doesn't give you a buffer because the chloride is free. But how is that different from these beakers? Well, you can see here, if I add a hydroxide, just like this step, I have 3 acetic acid, the protonated form. How many deprotonated form do I have? I have 1. Okay. It is different from the strong acid. Strong acid, the free anion, always the same, and it has all of it from the beginning, and it never change. Weak acid is changing. What does it change to? It actually changed to the deprotonated form. So when you keep adding, another proton could be pulled away, so you're down to 2, and this one will look exactly the same. In that case, will be 2:2 ratio. If you pull another proton away, you will have 1 left. The acetate will become 3, and you add 1 more, eventually all of them will be gone. So you add 4 hydroxide there, you end up with 4 acetate. So that's exactly why I have this here. Total acetate core. The amount of acetate would always be a constant. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. 3 plus 1 is 4. 4 plus 0 is 4. The difference is that how many of these acetate hold on to the proton. If all 4 of them hold on to the proton, you have 4 acetic acid. If 3 of them hold on to a proton, you have 3 acetic acid. 1 is just acetate core. If 2 hold on the proton, you have 2 acetic acid, so on and so forth. So this is a huge difference compared to a strong acid, strong base reaction, is that the protonated form become deprotonated form. The deprotonated form, I also call that acetate core, is the anion, is the A minus. So ultimately, how many A minuses hold on to a proton? That becomes the acetic acid. Okay. So this is the HA, this is the A minus. So just to clarify the language, this is what I meant by acetate core. Every single one of them has the acetate. That core hold on to a proton, that's acetic acid. Not holding to the proton, it's just acetate ion. Okay. So these terms are used interchangeably. Acetate ion, acetate core. Okay. I hope this clarifies a little bit what that means and why weak acid reaction is so different. This goes down just like strong acid, but the huge difference is on the anion. The free anion is increasing because hydroxide pull the hydrogen away to free this anion. Okay. Alright, so when you use same diagram, if I use 1 mole acetic acid and add 0.25 mole of hydroxide each time, you get this decreasing. The acetate ion is increasing. And this box right here is what we call buffer. it has both weak acid and conjugate base. When it's pure acid or pure base, you cannot have buffer. Okay. This goes back to the earlier question. It's missing link number 1. At the end of the reaction, what do you have left? 0 HA, 1 more A minus. Okay. This is true for weak acid. This is also true for strong acid. But the difference is amount of anion. Okay. Weak acid has the anion is basic enough to hold on to the proton. Strong acid, why is that strong acid? Because the anion just so weak that you cannot hold on to the proton. That is the difference between strong acid and weak acid. It's the basic strength of the anion. Okay. So just to clarify a little bit of the term we use, what is a buffer? Buffer is really a solution that resists the change of pH. So if you add some really strong acid or strong base into solution, the pH would not change much. And there's something very important, especially in biochemistry. Well, how do you make a traditional buffer solution? We use weak acid and its conjugate base, or you can use a weak base and its conjugate acid. This is typically the definition you learn. But we saw this. We saw the reaction right here. We are adding hydroxide to produce the conjugate base. Add more hydroxide, you produce more. Add more hydroxide, you produce more. So another way to do that is to sacrifice part of the acid. Meaning you have one part of acid, use some of it to react with hydroxide to produce its conjugate base. That will also get you the buffer solution. So this is one of the difficult thing to understand, but I hope the picture would actually clarify why this actually works as well. Oh, one last thing about conceptual understanding is this. We call that conjugate base. We say that weak acid, the reason it's weak because the conjugate base is basic enough to hold on to the proton. This actually shows you in the titration graph. The equivalent point is not at pH 7. Strong acid, strong base reaction. I'm going to show you the graph again. Strong acid, strong base reaction. The equivalent point is pH 7. Weak acid, strong base reaction. The equivalent point is greater than 7 because the conjugate base, think about, is basic enough to hold on to the proton. So it is not neutral, it is basic. And then one of the point is very important is the half equivalent point. This exists is because the weak acid was not dissociated at the beginning. So half equivalent point means 50% dissociated is part of the titration progress. While in strong acid, strong base reaction, you can never get 50% dissociated because it is 100% dissociated to begin with. You cannot go backward. Here, the dissociation is only very slight amount. So in the progress, you can get to 50%. So I hope this clarifies conceptually how strong acid different from weak acid when they react with sodium hydroxide. And we're going to talk about how to construct this titration graph in the next video. Alright, thank you for watching.